Hey guys, welcome back to Deep Shift Labs. I'm sure you have heard of some sort of recurring neural network. AI is making images, AI is completing text, AI is writing stories. I'm sure you've wondered how that works, and today I'll show you exactly that. So stick around and I will show you how recurring neural networks function from A to Z. So let's get started. Alright, so what will you learn in this video? Well, you'll learn what RNNs are, recurring neural networks. You'll learn how they function, some key mathematical notation that goes in it. Now, no, we won't get into the exact mathematics, but rather a sort of pseudo-mathematics to give you a more better intuition on how it works, rather than giving you an exact method of computing them. Why they're quickly being outdated, and what are some good alternatives and some good use cases for recurring neural networks. So let's get started. Well, what are RNNs? RNNs are recurring neural networks. They're called recurring because they're made to handle time series data. If you think about normal neural networks, and we'll get into this very soon, but dense layers take a set of inputs, which is an image, audio, text, anything like that, and provide one specific output. It might take an image and say that there's a 90% chance of a cat being in there, or take a piece of text and say the sentiment of this text is happy. Well, it's able to do this because it's taking one segment of data, computing it in a series of vectors. So if it had text, for example, we'd vectorize the text and compute a series of operations to get an output. We're not looking at what happened before that or what's going to happen after that. That is simply not possible with this modern scheme of dense layers and convolutions and things like that. So people thought of a new way to be able to look at time series data to create more accurate predictions, because I don't know if you've noticed, but life tends to move around time. If time doesn't move, then there is no meaning of life, at least to us humans. So if time is very important to us, we have to make it important to the AI as well. So how can we do this? Well, we can add something called recurrence, and we'll look at the mathematics later, but some implications of this can actually mean we can process video and audio. As you might know, audio, you can't take a single frame of an audio. Audio is always consecutive. You have to take a chunk of audio or sample the audio. You can't simply take one instantaneous point in time of audio. That's just a number. It has no meaning. As opposed to an image, that if you take a frame from a video, you can still have context. You can still make predictions off of that because that's simply an image. So the working principle is actually ingeniously simple. So how do they work? Well, let's say we'll take this classic example of processing a sentence, because that's usually the way RNNs are shown to beginners. So let's say with the sentence, I am a simple RNN. Well, let's say we have a dense layer here. We would feed in the word I. Maybe I is the number 4 when you vectorize it. And if you don't know what vectorizing or dense layers are, go check out our AI for Beginners video. It's a great starter's guide and will get you up to date with what all these key AI terminology, what it all means. So we feed in the word I, and it produces an output. We'll call it X of I, the output, because it's X at the value, Y at the value I. So, and then we do that again for AM, do that again for A, but we're not adding any context to it. So what AI engineers thought of was, what if we, instead of just using the weights of I, so all these weights that are going into all these neurons, those would be time independent, because they are only regarding these neurons, and although they get transferred over to a simple RNN, they don't have any intuition for time. So we'll add a separate set of weights called T of I, or rather in the next segment we'll call it H of I for a different reason, but we will add this variable that will be passed along, and it'll update its internal state. So those weights and biases that it has within it, it'll update that internal state as it moves along using a technique we will describe later to give it a better intuition for time. So now, not only is this AI considering what the word I am a simple RNN, what each of those words mean, but rather it's also taking into context what words came before it. So I came before am, so how did I change the internal state of the hidden network? And then as it gets passed along, how did am change the hidden network, the internal state of that recurrence? How did a change the internal state of the recurrence? And you can see as we keep on going along, each word adds its own twist. It adds its own signature to the internal state. And this is how we can provide a good intuition for time to an AI. So another way of thinking about this is that it's just a dense layer being unrolled. If you think of it as like a roll, then we're unraveling it to get the time series data as opposed to just clustering it all together and processing one in, one out. Now, there's another clever thing we can do. We don't have to predict each time the AI gets fed something. Let's say it gets fed I, but we don't want to predict. We want to analyze this entire sentence as a whole. Well, how can we do that? It's actually quite easy. Because we are having this recurrence, we're adding this prior context along all the way. And so, all we really need to consider is this end neuron right here. We can ignore all these other ones because all we care about is that final output. Another way of thinking about it is that the output is evolving as the sentence itself evolves. So we are basically giving it more context, letting it think a little bit more about it, and it's saying, okay, maybe this has a poor context, poor sentiment, oh, it has a happy sentiment, and we keep on evolving it. And again, the sentiment was just an analogy, another example, to explain how this works. And of course, if we were playing with images and we wanted it to generate a new image, the next image in the series, obviously we would take away this block here and let it predict each time to see if we feed an I, can it predict am? If we feed an am, can it predict a? That sort of situation. So this is a very extensible format. So what are some key mathematical functions that govern a recurring neural network? Now it's important to understand how dense networks work and how the mathematics behind that happens. So go check out our previous video if you're confused about any of this. So obviously we would need to compute the output. So y hat in this case of t, so t is a time interval, is simply a function of the hidden state, so that recurrent state, which is h hat of time minus 1. We don't know the hidden state of this time step just yet, and we're going to update that pretty soon. But we need to take that into consideration, as well as x of t. So what is the current input I'm getting? So we take f, which is a magical black box function, and we feed in the word I, which is x of t, and we feed in the current internal state of the recurrence, which is this other magical property that we kept on adding along. And then we take that and feed it all in, crunch an output, and that's going to be our final output to this red dot right here. Now, how do we update the internal state, you might be asking? So how we do this is we actually use an activation function like tanh, or hyperbolic tan, and we take the previous weights of that hidden state and add them to the current weights that we use to compute the output. And so by adding this together, we are adding that context, that latent space, in a way that the AI got from processing the input at that time with all the previous weights that we had. This is a very clever and very powerful technique in order to give recurrence. Now, this might seem a little confusing, but this t is actually just another representation of h. This bottom formula is the more common version, where we use h for the hidden state. I just use t because we're representing time moving along, so I thought it would be more intuitive to use t. So don't get confused, t and h are practically the same thing. Instead, t here is being used for time, t here is being used for that internal state. So I'm sorry if that's a little confusing. I just thought it would be easier for you to understand if t actually stood for time in the beginning. So why are they being outdated? You might say that this is a very powerful technique. I can see that this would work. Then why would we outdate it? Well, as a research paper published quite a while ago called Attention is All You Need, and they shook the AI ground from the bottom up. They introduced this idea of self-attention and transformers. Now, transformers are extremely complex machines that are way beyond the scope of this video, but I'll briefly explain. Transformers have this ability of taking any input, image, text, audio, anything, and using its ability to find key information within it. So in this case, it's able to take this sentence, which is in a different language, and able to translate it. And how can it do that? Well, it takes the key words in this sentence, because not all words in a sentence have to be necessary. So by using that, it's able to actually provide more output, more context than recurring neural networks can, because they're more flexible. And we have a video on transformers coming out soon, so if you're interested, like and subscribe. That's definitely on the way. But the ability for transformers to process a ton of data and make really powerful assumptions is what really shook the recurring network community down to the ground. Now, don't get me wrong, recurring neural networks are powerful tools when you have little amounts of data and you have simple tasks that need to be done very reliably and very deterministically. Absolutely go with recurring neural networks. They will do the job. If you want more stochastic results, and you want more powerful assumptions being made, transformer would be the way to go. So what are some good alternatives to recurring neural networks if you want to do data generation or anything like that? Now remember, if you want to predict on time series data and predict classifications, recurring neural networks are still the best for that. But if you want to produce new data, unique data, then you could use something called autoencoders or variational autoencoders. And some other AI networks that actually use RNNs as a base concept but modify them are this concept called RCNN. And that's the thing I've shown here on the right. RCNNs have this ability of using convolutions with recurrence to predict where objects are. Not just that they are in the image, that there's a human in the image, but exactly draw a bounding box. And that's probably what you've seen in images and videos of AI. It's probably this. So, now that you have a good understanding of RNNs, I would like you to go out there and try to program one. There's some good tools out there, some good research. Follow up, and if you have any questions or concerns, leave them in the comments below. Make sure to like and subscribe. It definitely helps the channel out. And if you have any other video topics or video suggestions that you want to see, leave them in the comments. We'll definitely make a video on it. Until next time, have a good journey with AI.